This lab is about the equilibrium of a solid due to three forces. I'm Lillian Adams, and I'll be going over our objectives. The objective of this lab is to master the static equilibrium of a solid under the influence of three concurrent forces, and to verify that the net torque will be zero using a force table and a rotational inertia apparatus.
Hi, my name is Isaac Cisneros, and I'm going to do the theory portion of this lab. Torque can be described in terms of linear force and its pivot location. The formula is T equals R times F, where F is the force and R is the distance from the pivot to the point at which the force is applied. For example, pushing at the far end of a door is easier than pushing near the hinges. And if you push directly towards the hinges, the door does not swing at all. There are two ways to find the torque generated by a force at an angle to the lever arm. First, we can split the force into its components and only take into account the component perpendicular to the lever arm for the equation. Another way to find the torque generated is by altering the lever arm to become perpendicular to the angle of the force. The direction of the force can be extended as a line of action. Then, a moment arm can be extended from the pivot to the point where it intersects the line of action at a 90-degree angle. The moment arm's length will be smaller than the actual lever arm and is the only one quantity relevant to the equation. Both of these methods are done with basic trigonometry and the SOHCAHTOA functions, where the magnitude of the force or the lever arm are the hypotenuse of a given triangle. Then, given the angle, either the moment arm or the correct component force can be found, depending on the situation and how it's modeled. For linear force, an object is at static equilibrium when the sum of its forces applied to it equals zero. We've calculated this in a previous lab by splitting each force into its components and adding each according to their dimensions. Looking at torque, we can assume that if we applied these same forces to a point on a lever arm, there would also be no torque produced. Torque is equal to the force times the length of the lever arm, but in this case the total force is zero in any direction. Therefore, the torque would also equal zero. The purpose of this lab, therefore, is to prove the relationship between linear and rotational equilibrium of a solid object.
The purpose of this experiment is to investigate the principles governing the equilibrium of a solid subjected to the influence of three forces. Equilibrium is a fundamental concept in physics. Equilibrium is achieved when the net force acting on an object is zero, resulting in a state of rest or uniform motion. By systematically applying forces of varying magnitudes and directions to a solid object, we will gain practical insights into the delicate balance needed for equilibrium. The investigation will involve the careful adjustment of force vectors and the measurement of resulting effects.
Hello, my name is Michaela Lohr. In this lab, we used a force table, paper, scissors, string, tape, pulleys, a set of various masses, a pencil, a ruler, and last but not least, our brains. To begin the methods of our lab, we set up a force table with 4 strings attached, then cut a 1-inch hole in the center of the paper, passed the 4 strings of the force table through the hole in the paper, and taped the paper down to the force table. We then positioned 3 pulleys at angles of 30 degrees, 180 degrees, and 330 degrees. Next, we adjusted the masses on the force table to achieve equilibrium. We put 80 grams on 180 degrees, 45 grams on 30 degrees, and 45 grams on 330 degrees, so that the vector sum of the 3 forces amounted to 0, indicating a state of static equilibrium. We recorded these mass values to their corresponding force lines drawn on the white paper. Then, we removed the paper from the force table and produced copies for each lab partner. Next, we selected a unique point on our copy of the paper to serve as a rotational axis. These points were chosen so that they would not align with the lines of action of the forces. We measured the lever arm distances for each force in centimeters from these rotational axes to the line of action of each force, and these measurements were noted on the paper. Using the lever arm distances, we calculated the net torque produced by each force about the chosen rotational axis. The calculations were performed in Newton centimeters. We also determined the direction of each torque, categorizing them as either clockwise or counterclockwise. The final step involved calculating the net torque for each rotational axis and estimating the absolute errors associated with these measurements.
Hello, my name is John Hargy.
On your sheet of paper, you should have drawn lines along the direction of the strings. These represent the force vectors. Make copies of this page for each lab participant. Also make sure that you have the corresponding mass for each force next to its line and calculate the force due to gravity, which is mass times the acceleration due to gravity. Here, I just wrote down 9.8, but make sure to use the full value of gravity in lab accurate to 5 significant figures. Next, select a unique point on the paper to serve as the rotational axis. This point should not lie on any of the lines of action of the forces. Now, this pivot point can be chosen arbitrarily because in a system in equilibrium, the net torque will be zero about any point. This is a consequence of the principle that if an object is in static equilibrium, then it is in equilibrium about any pivot points. Now, with a ruler, measure the perpendicular distance from the rotational axis you have chosen to the line of action of each force. This distance is the lever arm. Record these lever arm measurements here. Now the lever arm must be perpendicular to the line of action because torque is a measure of the tendency of a force to rotate an object about any axis. Only the component of the force that is perpendicular to the lever arm contributes to that rotation. Next, we're going to calculate the torque produced by each force about the rotational axis using the formula. Torque is equivalent to the lever arm multiplied by the force. Now here you must also decide if your torque is clockwise or counterclockwise. An easy way to determine that is to pretend that you're holding the paper here, and if this force was acting, it would naturally rotate the paper clockwise. And if these two forces were acting on the paper, they would pull the paper down counterclockwise. So therefore, this force is clockwise and these two are counterclockwise. This helps us when we calculate our net torque, because our net torque is going to be this torque subtracted by the other two torques. With this net torque, we can go on to calculate the absolute error, which would be our net torque, divided by the average torques, so these three torques, added up, divided by 3. All of this multiplied by 100 to give our percent error. After you do this whole process, repeat it 2 more times to have a total of 3 data points.
Hi, my name is Logan Johnson. In our experiment, we applied forces at angles of 30 degrees, 180 degrees, and 330 degrees, and carefully measured the resulting torques. We found 3 separate points on our paper and determined the net torque for each one of them. The ideal outcome for a system in perfect equilibrium would be 0, and we found the net torques to be 0.0661 newtons, 0.007347 newtons, and 0.00734 newtons. To find the accuracy of our experiment, we calculated the percentage difference and obtained it by dividing the observed net torques by the average of the mother values, which are the 3 calculated torques. The resulting percent difference was 2.36%, 1.6%, and 0.33%. These exceptionally low percentage errors signifies that our experiment was highly accurate. Potential sources of error could have included measurement variances, slight misalignments in force application, or unaccounted frictional forces. Despite these, the small percentage differences underscore the reliability of our findings, which align with the theoretical principles of rotational dynamics and static equilibrium. Through this experiment, we have gained a deeper understanding of how to apply torques and measure their effects, highlighting the importance of torque in analyzing the equilibrium of physical systems. We have not only validated these fundamental principles through our careful approach, but also appreciated their significance in the broader context of physical sciences. This experience has enriched our comprehension of the forces at play in static systems and the delicate balance that governs rotational motion.
There are many examples in everyday life where we see equilibrium due to three forces. But the example that I want to focus on is the balancing of a seesaw. The weight on one side creates a downward force. The weight on the other side exerts an upward force. The pivot point, or the fulcrum, allows for equilibrium if the weights balance. And that is how the seesaw becomes level.
Thank you for watching!